RENJITH B. NELLIYIL.
And today I am going to present the work which I am currently working on, and the heading of my presentation is the investigation of core architecture in bimetallic Zeolitic Immidazole framework using variable energy positron spectroscopy. And before going further, I would like to introduce the SIF material, which is a subclass of electro-organic framework which is having exceptional properties like chemical and thermal stability as well as easily tunable core architecture. And there are n number of SIF material. Among that, SIF 8 is studied extensively because of its exceptional properties. And SIF 8 we obtained by the reaction of zinc and 2-methyl. Another important SIF is the SIF 67, where we obtained by the reaction of cobalt and 2-methyl. And here we are going to explain in detail of these two SIFs in the upcoming slides. And we can use this SIF material for the separation of gases if I can make a membrane out of SIF. And there are two methods to synthesize a SIF-based membrane. One is I can deposit a thin layer of SIF material on a porous substrate like alumina. Other method is to incorporate the SIF material in a polymeric matrix. Here we are discussing on the first thin layer deposition and how the gas separation is happening in this case is like if we have a mixture of gas with a different molecular size, and one of the gas having a molecular size lesser than the pore aperture of this SIF material, like 3.4 Angstrom, then only that particular gas will pass through. The bigger size gas molecule will not pass through the membrane. This is how the separation is happening. But this is in an ideal case. In the real situation, we have to face these two limiting factors. One is the intercrystalline void, another one is the framework flexibility. So if I try to deposit a SIF material in a porous substrate, there will be some intercrystalline voids through which the larger size molecule will also pass through. Another is the framework flexibility. So if because of the gas molecule interaction with the SIF material, the pore size may increase. So by these two limiting factors, my efficiency of separation is getting seriously affected. To tackle this issue, I am going to use two different strategies, and I am using a combination of these two different strategies. One is the fast current driven synthesis, another one is the mixed metal strategy. And these two strategies are known for the separation of flexibility of the Zeolitic Immidazole frameworks. In the case of mixed metal strategy, I cannot use a large amount of cobalt because the crystalline kinetics of this cobalt is very high, so that it will form larger crystals. Again, the intercrystalline void issue will come into picture. Okay, so to get an optimum condition with the flexibility as well as the intercrystalline void, I prepared 7 different mother solutions with varying zinc and cobalt ratio, and the whole idea is to replace some of the zinc with cobalt. That's it. And this is the synthesis procedure will be used to synthesize a thin layer of SIF material on a silicon wafer. And here we place the silicon in the negative terminal, and we pass 10 microamperes of current for 30 minutes, constant current for 30 minutes. And these are the photographs of the sample which we prepared. And to check the phase purity and chemical bonding, we did the XRD and FTR. Here you can see all the 7 samples having similar structure, similar topology without any impurity, and the FTR also clearly shows that the chemical bonding is intact. Now the low magnification SEM image clearly shows how uniformly the SIF material is deposited throughout the silicon wafer. And in the high magnification image, you can see densely packed underground crystals. I did the cross-sectional SEM analysis, and you can see how beautifully the SIF material deposited on the silicon wafer. And this is the interface between silicon wafer as well as the SIF material. In fact, I don't want to put this line because that will destroy the beauty of this image, natural beauty of this image. And I did the line scanning of this from one end to another end, and from that I understood around 16 micrometer thick film I can deposit on the silicon wafer. And from the EDS mapping analysis, I understand that the cobalt and the zinc is uniformly mixed in the throughout the material, and which again confirms that the microscopic level mixing of zinc and cobalt is achieved. And finally, I need to know how the pore architecture is changing because of the mixed metal strategy. The best tool I can use to study this one is the positron annihilation spectroscopy. And here we are only discussing about the Doppler broadening spectroscopy. And when the positron interact with the electron, it will annihilate each other and it will give photon heavy gamma ray. When a positron interacts with a high energy electron, the Doppler broadening will happen. And this is the central part of the Doppler broadening, and the area under this particular region is called as S parameter. And the S parameter has a direct correlation with the number of pores or the size of the pore in a porous material. In short, I can say if the S parameter is higher, then I can say the number of pore or the pore volume inside the material will be higher. Now, this is the instrumentation we use for the study. This is the variable energy positron spectroscopy, where I can where I can accelerate the positron accordingly, and I can implant with different depth according to the accelerating voltage, so that I will get an idea about the pore architecture in terms of depth. And this is the instrument which I am working on, and these are the SE profile which we obtained for the pure 68 and pure 67. And you can see there is an increase in the S parameter for both 68 and 67. What exactly happening is, when I am increasing the implantation energy, more and more positron are annihilating inside the sample without going back to the surface. And at a particular point, whatever number of positron I am pumping into the sample, all are annihilating inside the sample. So that's why it is getting saturated. Now, when I am comparing the 68 with 64, the higher S parameter observed for this 67 because of the larger intercrystalline void. So now you may understand that the importance or the significance of this particular technique, which I can use for understanding the pore architecture of these porous materials. And finally, I just want to correlate this with the mixed metal samples which I synthesized using mixed metal strategy. Now, if I reduce the cobalt concentration by 25%, the S profile is getting reduced, which means the intercrystalline void is getting reduced. And again, if I reduce to 25%, the concentration of cobalt to 25%, the S parameter is again reducing, which clearly shows that the mixed metal strategy is the best way to tune the pore architecture of this particular SIF materials. And secondly, the variable energy positron spectroscopy is the best tool to analyze this pore architecture of this material. And finally, I checked the temperature stability of this pore architecture. I heated the sample at 100 degrees Celsius and in an open air atmosphere for 30 minutes. For SIF8, there is no change happened in the S parameter, but in the case of 67, the S parameter is decreased after the heating, which is a very interesting observation, because simple heating itself is improving the intercrystalline voids here. And we've done the same analysis for all the other samples. Now, except this zinc 75, cobalt 25, all others are having the similar S parameter. And I can conclude my work in this way, like we successfully synthesize and deposit the bimetallic film on the silicon crystal. The phase purity and chemical bonding of the film is understood from the XRD and FDAR. We significantly modified the intercrystalline void in mixed metal SIF confirmed by the variable energy positron spectroscopy. And these are the future scope of my work. And I would like to acknowledge my dear guide, Dr. Sandeep Kumar Sharma, as well as Kathy Sudarshan sir, P.K. Mohammed sir, and Anand sir for their support.
So now it's open for any questions.
Mr. Renjith,
Yes.
Why do you have selected zinc for replacing cobalt? First of all.
Actually, sir, it is the vice versa. CIF8 is the mostly studied material which we obtain by the reaction of zinc and 2-methyl. And here I am trying to replace some of the zinc with cobalt because the cobalt and linker bonding is more stronger. So the flexibility will get reduced. That's the motive why I choose cobalt to replace some of the zinc.
And what could be the reason for that anomaly for one particular combination, that 75
Yes, sir.
75 part of zinc and
25. This one you are saying, sir?
yeah.
So here what we done is we check the thermal stability of the pore architecture. Here what we observe is the decrease in S parameter, which means in this particular case also, like 67, the intercrystalline volts is getting reduced by the heating effect. Like what we are exactly doing by heating is the vibrating the molecules, right, sir? So the intercrystalline voids are getting reduced because of this one. But when we are considering all other samples, we could not observe this in that particular thing.
There are commercially available membranes
Yes,
for separation of different constituents, like hydrogen and other things, right?
Yes.
So, in comparison to those commercially available membranes, what advantage that you are postulating for this zinc material?
Yes, sir. The people are extensively studying and trying to use this CIF8 membrane for the separation of especially carbon dioxide and methane. If we produce the biogas, in that biogas, if we can reduce the amount of carbon dioxide, that will be so much helpful. But still, we are not able to achieve that much good separation because of the intercrystalline void as well as the framework flexibility. So, this is also a part of that work to increase the efficiency of this particular membrane. That's what we are doing. And most importantly, I'm trying to correlate how the changes in pore architecture because of these tuning with cobalt and then FCDS, how the pore architecture is varying experimentally by a method called variable energy positron spectroscopy. These two are the most important part of my work.
Very nice presentation. One of the applications that you have mentioned is gas separation.
Yes.
So with your membranes, have you tried doing that, or that is not a part of your work?
No, sir. Actually, it is in our scope of the work. Basically, we studied how, because of this tuning, how the pore architecture is changing by using our variable energy positron spectroscopy. Now, the second part, we will deposit this CIF material in a porous membrane like alumina or something, so that we can do the gas separation study.
Okay, so that is the scope of work, but we have not yet done it.
Yes, sir. No. This is the scope of work. Yes.
Oh, fine. But you have not carried out it yet.
No, sir. No.
Fine. Now, related question is, you have suggested it for gas.
Yes.
Now, suppose I have a liquid with ions.
Yes.
Two different sizes. Is it possible to separate these two ions?
Yes, sir, that's a good question. Like, here the separation is happening based upon the size. If the ionic size, if you have an ions with the size which is one ion have a size lesser than the pore aperture and another one is having a size which is higher than the pore aperture, then we can separate. Or else it will be very much difficult.
Suggesting that. So is it possible?
No, sir, it is not possible because ions are too small. Too small to separate.
Okay, now last question is, how consistent is your method of preparing this membrane? Is it very consistent?
Yes, sir, obviously.
Have you tried that, or you are just guessing? Have you tried making several batches of your membrane?
Yes, sir, obviously. We actually synthesize more than 10, 12 number of substrate for different analysis. For example, if I used this membrane for SEM analysis, at least we have to put a minimum 3 to 5 nanometer thick gold in the sample. So I cannot use that particular sample for any other analysis. So I prepared number of samples, and for every sample we are getting this much good thick film in the silicon. So it is highly required.
Okay, thank you, Renjith. So we move on to the next speaker. That is by Sri Meghnad Sen.